Hello everybody, Mr. Hasty here again. Today we're going to be starting chapter 7.5, which is applications of integration in physics and statistics. So we're going to break this up over three sections mainly. The first one is going to be the concept of work in physics. Second one is going to be fluid dynamics, which is work with fluids and pressure with fluids. And the third section is going to be on statistics. So, for those of us who haven't taken physics before, we're going to talk about what work is. Work is defined as force applied over a distance. So the big thing to understand here is that a force needs to be applied and distance has to be achieved. If you push on a wall and that wall doesn't move, you have done zero work. We worked with this a little bit when we talked about Hooke's law earlier this chapter, but it's been a minute. There are two formulas we'll use. The first one is that work equals force times a distance, and we'll call that distance x. We could call it y, we could call it d, but it's always force times a distance. And that works very, very well for a consistent amount of force applied over a distance. But if the force is changing in any way, then we have to use an integral. If the force is changing in any way, we have to come up with a formula for force in terms of x. And when we integrate that formula, that will give us the amount of work on a given system. Now the units for force are the units for force are a newton or a pound if you're in the English system. So the units for work are typically measured in newton meters, which is also known as joules. And in the English system, it's typically feet times pounds, and it's literally just called a foot-pound. Now, one of the things we have to talk about is the concept of weight. Weight is a force. It's the force applied by gravity. So we will list weights in pounds or in newtons, and that is to be used as the force in a given problem, or part of the force in a given problem. So we're going to look at one big example which kind of covers all these concepts. So example, a 35 Newton empty bucket is being filled from the ground to a height of 15 meters. The rope attached to the bucket weighs 0.55 newtons per meter. Let's take a second and talk about what that means. If we have a rope, it's saying that every 1 meter of that rope weighs a certain amount. It weighs 0.55 newtons. And why that's important is when you start and the rope is long, you're going to have more weight to pull than when you've almost pulled the bucket all the way up and the rope is short. The bucket starts with 85 newtons of water, but due to a leak is only half full when it reaches the top. So here's another situation in which the amount of force required changes. It takes more force to lift the water when we start, but because of the leak, there's less and less water, which means it requires less and less force. So we're going to find the amount of work done on A, just lifting the bucket, B, lifting the rope, C, lifting the water, and D, lifting the entire system. So let's do a real quick picture here. So we have a rope up on a platform, and that rope is coming down and attached to a bucket which has some water in it. Now, as we lift that up, the rope's going to get shorter and shorter and shorter. Let's do a second picture here. So we're going to have less rope, and due to the leak, we're going to have less water as well. So the bucket is consistent, but the rope and water are both changing as we go up in distance. So let's start with part A. Part A is going to be very straightforward. The bucket itself, the amount of force required to lift that bucket is always 35 newtons. It says the bucket is 35 newtons when empty. So the force that it takes to lift it is not changing. And we're lifting it to a height of 15 meters. So we can use the formula work equals force times distance. I'm going to use y here because we're going upward with our distance. You could use x, you could use d. So in this situation, we have a 35 Newton bucket being lifted 15 meters. That's going to get us 525 Newton meters, or we're going to say 525 joules. Okay, that part's done. Part B. Now we're going to do a simplification here. It doesn't tell us where the rope is attached, and that would affect the initial height of the rope. We're going to assume that we start with 15 meters of rope, the entire distance listed in the problem, and at the end we have 0 meters of rope. So, how are we going to model this? Well, we can write an equation for the weight of the rope based on how much rope is out. So the force required, so we lift y, well let's think about what would be true at 0. When we've pulled up y meters of rope, we are going to have all the rope. We're going to have 15 meters of rope. And it says it's 0.55 newtons per meter. So at the very beginning, we're going to have 15 times 0.55. That's how much rope we're going to start with. Then we're going to go down by 0.55 newtons every meter. So let's think about this equation, because this equation setup is really, really important. The fundamental idea here is we have a certain amount of force to start with. That would be all the rope we need, all 15 meters of the rope, 15 times the 0.55 Newton meters. And then we're losing a certain amount every meter. We're losing, as it says, 0.55 newtons every meter. So we're going to call that 0. That sounds like a slope, newtons per meter. So in our equation, in our linear equation, it ends up being a slope. So I'm going to simplify this equation a little bit. And we get 8.25 minus 0.55y. So how do we use this? Well, since this is not constant, we have to use the integral. The integral form of work is the integral of f of y dy. So that'd be the integral of 8.25 minus 0.55y dy. Now, what would our bounds be? Well, we're going from a point where we are on the ground, we're going to call that 0, to the point where we're at the top of a 15 meter building or surface, whatever. So we're going to call that 15. So our bounds here are going to be from 0 to 15. And we do that integration. We could do it by hand, but I'm just going to use a calculator here. And I get 61.875 joules. Now, what's important to note here is that the amount of work it takes actually goes down as you lift the rope. And remember, we're just talking about the rope here, not the bucket, not the water. And so it goes down as you go. So you can't just do it as one number. You have to do it as an integral of a function. All right, I'm going to clear this and record our values for our first two parts, and then we will continue with part C. Alright, so I cleared it out and I recorded at the top here our responses, our answers for A and B. Looks like 1525, but it's actually 525. So, part C, lifting the water. So the water starts with 85 newtons, but due to a leak, it is only half full when it reaches the top. So I'm going to write an equation here, and to do that, I'm going to use points. When I start and my bucket is 0 meters off the ground, I have 85 newtons of water. So these values are Y, which is weird because we usually don't have Y in that position, but that's our height. And this is an amount of force. Now, when I get to the top, which is 15 meters off the ground, I'm going to have half that. Well, half of 85 is 42.5. I'm going to use those 2 points to create an equation. So, first thing I'm going to do is find the slope. And we get 42.5 minus 85 over 15 minus 0. And we're going to get a negative slope, and that makes sense because we're losing water, which means we're losing weight. So as we do that, we get negative 2.83 repeating. And that becomes the slope. We already know our y-intercept, 0.85. So the amount of force in terms of y that I'm going to have is going to be 85 minus 2.83 repeating y. So that means I start at 85 newtons and I lose 2.83 repeating every 1 meter I go up. So to find the amount of work it is, we use the integration formula. Again, our bounds are going to be 0 to 15. Now, one note as you're putting this into your calculator, one thing people forget is that you do need to make sure that your window actually goes from 0 to 15. And I get 956.25 newtons. All right, part D is as simple as you think it could be. For the entire system, all you have to do is add up the parts of the system to get the total amount of work done. So we have our bucket plus our rope plus our water made a mistake here. This should be joules. Sorry about that. All work is measured in joules or foot-pounds with rare exceptions for other units. $1,543.125 joules for the whole system. All right. Now, the next time we talk, we'll be talking about work having to do with liquid movement, and we'll also be talking about liquid pressure. And so, see you guys next time.